Hello, everyone, and welcome to this AP Chemistry virtual lesson. If you are joining us for the first time today, that's great. We're glad you're here. Thank you for watching. If you have already watched the two previous lessons that were presented this week, super, welcome back. And we're happy that you have been a consistent viewer. I would like to remind everyone that this is day 3 in our series of lessons on AP Chemistry. These virtual lessons will be presented daily, Monday through Friday. We began on Wednesday, March 25th, and this series of lessons will run through Friday, May 1st. My name is Michael Faribaugh, and I teach AP Chemistry at Albemarle High School, go Patriots, in Charlottesville, Virginia. Good morning to you. It's 10 o'clock in the morning where I am, and I want to say that no matter where you are in the world or what time it is for you right now, each of these virtual lessons in AP Chemistry will be recorded and available for students to watch on this YouTube channel at any time. As I mentioned on Wednesday, this is a virtual lesson, which means this is a different experience from what I would normally do in my own classroom. In my class, I would be able to walk around the room and check on student work. Students would be able to ask me questions during the lesson. During these virtual lessons, I will make every effort to present the information clearly. I will give you examples and diagrams and practice problems that are designed to help you better understand the content and skills in the AP Chemistry curriculum. Today's lesson will cover topic 8.3, which is on weak acids and base equilibria. During today's lesson, if you are in the middle of solving a problem or thinking about what the correct answer is, and I, your teacher, start explaining the answer to the problem before you are ready, please feel free to pause the video. Give yourself time if you need to answer the question that appears on the screen, and then when you're ready, you can click play and see if your answer is correct. I mentioned this on Wednesday, but I would like to say it again for any new people joining us for the first time. For more information about AP exams, you can visit the following website, apcentral.collegeboard.org. And at the top of the page, you can click on the link that will give you more information about how the College Board is supporting schools that may be closed right now. You may have already heard that in AP Chemistry, the exam this year will only cover the material in units 1 through 7 from the course and exam description. That being said, people watching this lesson today might be asking the following question. If only content from units 1 through 7 will be tested on the AP exam this year, why are we learning about a topic from Unit 8? Well, today, the topic that we are covering, 8.3, acid-base equilibria, is one that colleges have asked all AP students to study, even if it will not be tested on the exam in 2020. Colleges are supporting AP students this year by allowing a more flexible approach to the exam, where it will focus on a lesser amount of content than in other years. To make this relevant to your upcoming AP exam, I will include AP exam practice questions in today's lesson. And there are lots of connections between topic 8.3 and topics from earlier units, such as Unit 3, intermolecular forces, Unit 4, chemical reactions, and Unit 7, equilibrium. Those units are important and will be included on the AP exam. Eventually, the full schedule of review topics for the remainder of this course will be made available to you so that you, the student, can choose which topics you want to prioritize for review and thus which virtual lessons you'll want to watch. Well, I'm ready if you are. If you happen to have a pencil or a pen, scratch paper, and a calculator, great. If you need to pause the video right now so you can go grab those items, feel free to do that. Now, let's get started. So in this lesson, you will learn about the following topics and skills. 8.3, weak acid and base equilibria. And the skill or the science practice, explain the relationship between variables within an equation when one variable changes. Today, we'll touch upon topics from Unit 3, such as solutions and mixtures, especially molarity. We'll do calculations along with the paying attention to significant figures in today's lesson. From Unit 4, which is on chemical reactions, we'll talk about net ionic equations. We'll talk about stoichiometry, mole relationships. We'll talk about titration, and of course, acid-base reactions. And because it's weak acids and weak bases, a lot of topics from the Unit 7 equilibrium, the calculations of the equilibrium constant, the magnitude of that constant, and Le Chatelier's principle will definitely be addressed. So today we'll talk about the difference between a weak acid and a strong acid. We'll talk about the Ka expression, the acid dissociation constant for a weak acid, the relationship between the magnitude of the Ka or the pKa and the strength of the acid. And of course, we'll talk about bases as well. So weak bases and the Kb expression and percent ionization. All right, now our warm-up today is going to be the problem that Mr. Byrne presented in yesterday's lesson. So this was from 2014, and we have propanoic acid. Now, propanoic acid, there is the formula. You might be wondering whether propanoic acid is a strong acid or a weak acid. Well, something that you should know from the AP Chemistry curriculum are that these 6 formulas represent the strong acids in chemistry: hydrochloric, hydrobromic, hydroiodic, nitric, perchloric acid, and sulfuric acid. Since clearly propanoic acid is not on that list of 6 strong acids, we know it is a weak acid. In this particular problem, it says if the pH of a hydrochloric acid solution, which again, we know that HCl is a strong acid, has the same pH as that of a propanoic acid solution, then the statement says that the molar concentration or the molarity of the hydrochloric acid solution must be less than that of the propanoic acid. Now, for this particular problem, we can pick any pH we want. I'm going to pick 2.79 because it's right there in the problem. As far as the concentration of propanoic acid, that is also stated in the problem as 0.2 moles per liter. But we don't know the concentration of the HCl. Now, you might wonder, could the concentration of hydrochloric acid also be 0.2 moles per liter? Well, not likely. If you remember the lesson from yesterday, the pH would have to do with the negative log of the hydronium concentration. And for a strong acid, that is the concentration of hydronium because it's 100% dissociated in water. So take a moment on your calculator and do the negative log of 0.2. If you do the negative log of 0.2, you would get a pH of around 0.70. So clearly, a 0.2 molar solution of HCl would not have a pH of 2.79. All right, how would we take a pH of 2.79 and turn that into a concentration? Well, if this is our formula for pH, but we already know the pH and we're trying to find the concentration of the hydronium ion, which essentially is the concentration of the HCl, then we have to do the opposite of that log base 10. So 10 raised to the minus 2.79. So do that right now on your calculator. Take 10 raised to the minus 2.79 and see what you get, because your answer will be the concentration of HCl. All right, well, if you have done that math on your calculator, then you should get a concentration of 0.0016. Now let's compare those two concentrations. The concentration of the HCl is much less than the concentration of the propanoic acid. Well, that looks like that statement is true. HCl is a strong acid that ionizes completely. So therefore, fewer moles of HCl would be needed to produce the same hydronium concentration as the propanoic acid solution, because propanoic acid, being a weak acid, only partially ionizes. So we need fewer moles of HCl to achieve that same concentration. All right, there was another question that Mr. Byrne talked about yesterday, and this relates to pH. We have 4 acids, 1, 2, 3, and 4. Remember that the strong acids are listed there at the top of the screen, And they say in this question, which of these 4 acids is hydrochloric acid? So I'm going to go ahead and take the negative log of this particular concentration. And I can do this on my calculator, or I could actually do this in my head. It turns out that 0.01 is 10 to the negative 2 power. And so if you take the negative log of 10 to the minus 2, then you would get a pH of 2. So I think that this is our strong candidate for being hydrochloric acid. Let's continue. Take the negative log of 0.1 on your calculator, or you could do this in your head, because 0.1 is 10 to the minus 1. You get a pH of 1. And you may already know from math class that the log of 1 is 0. So correct answer, which of the 4 acids is hydrochloric acid? It looks like it's going to be acid 2, the second one in the column there. Now you might have had another way to figure this out, which is just simply look at these 4 acids. If any one is going to be hydrochloric acid, the strongest acid should have the lowest pH. So if one of them is hydrochloric acid, it would be the one that consistently has the lowest pH of all of the concentrations that were checked. All right, let's move on to what you need to know about topic 8.3. So I mentioned we're going to talk about weak acids today. The difference between a weak acid and a strong acid, as I've already mentioned, is that a weak acid only partially ionizes, whereas a strong acid is completely ionized in solution. So in general, the majority of the molecules have not broken up into H+. So let's go ahead and write a weak acid as HA. It would react with water. It would transfer the H+ to the water, and it would produce hydronium. And then after that transfer had occurred, you'd be left with A-. Whatever A is just simply the negative ion. Like for example, A could be fluoride, or it could be nitrite, or some other negative ion. So on the left, we have 1, 2, 3, 4, 5, 6, 7 molecules of HA that have not lost the proton. And on the right, you can see that every single molecule of HA has already been split up. So the molecules that are shown and the ions on the right, that would be a strong acid, which is 100% ionized. Whereas on the left, this would be a weak acid because it is only partially ionized in solution. Well, if it's only partially ionized in solution, then we're going to talk about the equilibrium constant. Again, I mentioned unit 7. So we're going to be talking about the equilibrium constant for this reaction. So here, as I mentioned, the HA transfers a proton to the water molecule, and you get the hydronium ion. And then what we're going to call A- would simply be the negative portion of the molecule, the -1 charge. So that particular expression, the Ka expression, has to do with the equilibrium constant for this reaction. Now, normally, if we're talking about concentration, we put that in brackets. That would be the concentration of the products divided by the concentration of the reactants. That's how we typically set up an equilibrium expression. Now, there are no coefficients to worry about in this expression, so we're not raising things to the second or the third power. But you might notice that there are 4 chemicals. One of them, water, is a pure liquid. Pure liquids and pure solids cannot be expressed in this equilibrium constant expression because they don't have a concentration. Pure liquids and pure solids are excluded from the equilibrium expression. So therefore, we're going to have the concentration of hydronium times the concentration of this conjugate base, the A-, divided by the concentration of HA, and that's it. The water is not included. Is there an equation sheet that you guys will have available on the AP exam? Absolutely, and I'm showing you a portion of this equations and constant sheet, and if you look closely, there are a number of different equilibrium expressions, but one of them that I just circled, that's the Ka expression. Whether it's H+ or H3O+ hydronium, that means the same thing. So you have your products, overreactants, and again, notice that water is excluded from that expression. All right, well, I'm going to give you two examples of a weak acid. We have acetic acid, which is also known as vinegar, and then we have hydrofluoric acid, which has the formula HF. These are not on the list of strong acids. They are both classified as weak acids. Which of these two weak acids is the stronger acid, and how can you tell? Now, if they're going to be strong acids, they'd be 100% dissociated. We know that neither of these is a strong acid. They're both weak. So these are both weak acids, but the question is asking, which of the two is stronger? The answer is you actually can't tell from what I've given you so far. You'd have to be given a little more information about things like pH or percent ionization, or in this case, the Ka. Let me go ahead and put the Ka values up on the screen. All right, take a moment to look at those two Ka values. They are both less than 1, very consistent with the fact this is a weak acid for each one, but compare the magnitude of these two K values, and what do you notice? Well, hopefully you notice that one of them has a larger Ka value than the other. So that means that the larger the Ka value is, the stronger the acid is. The larger the magnitude of Ka, the stronger the acid. There's something else on this screen. It says the smaller the value of the pKa. Now, pKa would equal the negative log of the Ka value. And again, the pKa, that formula is also on the equation sheet that I showed you earlier, okay? So again, the idea that we have something called the pKa, which is the negative log of the Ka. All right, so what it says is the smaller the value of the pKa, the stronger the acid. Well, I'm going to ask you to take the negative log of this Ka, but I'm going to modify it slightly. I'm just going to go ahead and scratch through this for now. Can you do this without a calculator? Absolutely. Just focus on the exponent. The negative log of 10 to the negative 5, it'd be 5. And the negative log of 10 to the negative 4, just be 4. That means, as I said earlier, the smaller the value of the pKa, the stronger the acid. We already know that HF was the stronger acid because it had a larger Ka. You can go ahead and pick up your calculator now and do the math. Go ahead and type in the negative log of 1.8 times 10 to the negative 5. And if you do this, you're going to get around 4 point something, okay? What I did on my calculator is I got the pKa for acetic acid. It was around 4.74. If you take the negative log of the other Ka value, which would be 6.8 times 10 to the negative 4, put that in your calculator. The negative log of that number should be around 3 point something. When I did that on my calculator, I got around 3.17. So consistent with the information, if you compare the pKa values, the one that has a smaller pKa was the stronger acid. Now again, for those of you that might be thinking, this is topic 8, that's excluded on the AP exam. If you go back to unit 7, which is definitely covered on the AP exam, one of the topics in unit 7 on equilibrium is to talk about the magnitude of the equilibrium constant. So AP chemistry students should be able to compare the K value, the equilibrium constant, for two different reactions and make a conclusion based on what information tells us about the strength of the reaction from left to right. So again, that's information that's important to know for equilibrium. All right, let's talk about bases. You could have a weak base. Now I'm showing you a molecule on the screen here. I'm just going to call it B for base. This might be ammonia, or it might be methylamine or other weak bases. It would act as a proton acceptor. So one of the H+ ions from a water molecule would get transferred to the base, and you would form, for your products, Hb+, that would be the conjugate acid of that base, and the hydroxide ion. Again, because it's a weak base, it's not completely ionized in solution. It's only partially ionized. So therefore, we have a K expression. Remember that the water would not be included in this expression because it is a pure liquid and doesn't have a concentration. You'd have the concentration of the conjugate acid times the concentration of the hydroxide divided by the concentration of the base. Do they give you this equation on the AP equations and constant sheet? Absolutely. It's right there underneath the Ka. There's the Kb. So it's nice to know you have access to these equations, and it's also nice to know that you understand the meaning and where they come from. All right, next thing I would like to talk to you about is percent ionization. So look at the particle diagram that we have here on the screen. I'm going to go ahead and circle. How many acids do we have? 1, 2, 3, 4, 5, 6, 7. Technically, we have 8 acid molecules, but one of them, only one of them, has dissociated, split up, ionized, and formed a hydronium ion. So what we have is a weak acid that has been ionized, but only a little bit. And you can do this either on your calculator, or you might know that the fraction 1/8 is 0.125. So therefore, this is roughly about 13% ionized. So how do you define the percent ionization with a formula? Well, we define it in this way. This was our Ka expression. I'm just adding the little subscript here, original, to remind you that this is the concentration of HA that would be given in the problem or possibly listed on the bottle of chemical if you're looking at this in the lab. So the ratio of the concentration of the hydronium ion divided by the original concentration of the acid times 100, that is your percent ionization. So I just did it in the previous screen. I said it was around 13%. You would get information from the problem where you could have molarity or pH, and you could figure this out. Now there's also the equivalent ratio for a base. It's not going to be hydronium, but rather hydroxide, the concentration of hydroxide divided by the original concentration of the base times 100. The percent ionization of a weak acid or a weak base can be calculated based on the given information. So they might tell you the Ka or the pKa. They might give you the initial concentration of the acid. So for example, the concentration of whatever that acid happens to be, and then you could calculate that ratio. You could figure out the percent ionization for either a weak acid or a weak base. All right, we're now going to move on to some guided practice. I had mentioned that net ionic equations were covered in topic 4.2. That would be unit 4. It's on chemical reactions. 3 different acid-base reactions are shown. For each of these reactions, I'd like you to write the net ionic equation. This would be a good time. If you need to pause the video, then you could write down these reactions. You could think about how to represent each of these substances as either a molecule or as ions if they are extensively ionized in solution. And then you would cross off what we call in chemistry the spectator ions on both sides. So any formulas for ions or molecules that appear unchanged in this reaction will get crossed off. All right, so I have 3 reactions. These are all acid-base reactions. Here we have an acid. This is propanoic acid. Here we have a base, potassium hydroxide. Here we have an acid, that's nitric acid. Here we have a base, calcium hydroxide. Here we have an acid, hydrobromic acid, and then this would be the weak base. This is called dimethylamine. In each of these reactions, a proton is transferred from the acid to the base. In our first example, the proton will get transferred to the hydroxide ion to make water. In our next example, the proton will get transferred to the hydroxide ion again, but because we have 2 H pluses and 2 OH minuses, we're going to make 2 water molecules. In our third example, there is no water on the right side of the equation. That's because the base is this molecule. This is like the equivalent of what I showed you earlier. This is like the Hb+. So this portion, which I guess you would call the dimethylammonium ion, that would be the conjugate acid of the base. All right, so I'll give you a moment to write down these reactions and to figure out the net ionic equation. I will also mention that because they are acid-base reactions, everything is soluble. There are no precipitates to worry about. Students should know, if we were talking about precipitation reactions, which again, we are not talking about that today, that's from topic 4.7, that if you contain a sodium ion or a potassium ion or ammonium or nitrate, you will definitely dissolve in water. But again, no precipitates here. Your job is to decide, should I split this up into ions or not? All right, well, if you have copied down these three equations, we're going to take them one at a time. So I'm going to start with the first one on the next slide. The strong acids, HCl, HBr, HI, HNO3, HClO4, H2SO4. Propanoic acid is clearly not a strong acid, so it's only partially ionized. From yesterday's lesson, 8.2, we talked about strong acids and strong bases. If you have a soluble compound that contains hydroxide, that is a strong base. That completely, I guess I would say, dissociates, splits up into K plus and OH minus. On the right side of the equation, even though I have written it as one formula, it actually contains a cation and an anion. Well, the cation is the K plus, which came from the potassium hydroxide. The anion is the propanoate, that is the conjugate base of the propanoic acid. Everything is soluble. So should we split up a weak acid if it is only partially ionized, or should we leave it together as one formula? Well, hopefully you answered, we should leave it together. Again, it's a weak acid. The majority of those molecules have not been ionized. Of course, for a strong base, it's very soluble. It's an ionic compound. It definitely dissociates into cations and anions. We're not going to split up water. Water is a covalent molecule that is not going to be broken up into ions. And then we have this soluble ionic compound that contains both potassium ions and this propanoate, the conjugate base of propanoic acid. Remember, let's cross off any spectator ions that appear on both sides. And once we do that, we have our net ionic equation. All right, our next example was the nitric acid and the calcium hydroxide. You know that nitric acid is on your list of 6 strong acids. Let's go ahead and split that up into separate ions. So we'll have H plus and NO3 minus. Calcium hydroxide is a soluble ionic compound. We should split that up. That's a strong base. We're not going to split up the water. And the calcium nitrate is a soluble ionic compound. All nitrate compounds are soluble. That contains calcium ions and nitrate ions. So let's split up the nitric acid, and because of the coefficient of 2, I have 2 H pluses and 2 NO3 minuses. Let's split up the calcium hydroxide. So we have 1 calcium ion and 2 hydroxide ions. We're not going to split up the water. And then we have the calcium and the 2 nitrates. We'll split that up as well. We'll cross off our spectator ions, which means I see nitrate on both sides. Let's get rid of that. I see calcium on both sides, get rid of that. And then what we're left with is H plus and OH minus and water. Of course, each coefficient is 2, so we can go ahead and just reduce that to a 1:1:1 ratio. All right, one more example of a net ionic equation involving acids and bases. This time we have a weak base and a strong acid. So HBr is definitely on your list of 6 strong acids. We're going to split that up into H plus and Br minus. Remember that the proton was transferred from the acid to the base. So we're going to form the CH3 parentheses 2NH2 plus, or the dimethylammonium cation, the conjugate acid. And then of course, bromide comes along for the ride as well. We are not going to split up a weak base because it is only partially ionized. We're going to definitely split up the H plus and the Br minus because it is a strong acid and fully ionized. And this is a soluble ionic compound with the conjugate acid being a cation and the Br minus, the conjugate base of hydrobromic acid. It's on both sides. We're going to cross that off as a spectator ion, and we have our net ionic equation. Now, something else we can talk about is how do we calculate the value of Ka? Because it's nice when they give it to you in the problem, but if we had to calculate the value of Ka, how would we do that? Calculate the value of Ka for acetic acid. It is a weak acid, so we're talking about this. Ka is equal to H plus, or you could write hydronium, times the concentration of A minus, which in this case is the acetate ion right there, and then divided by the concentration, the original concentration of the acid, which would be this, HA. So we know the number on the bottom. We know that HA is 0.1. Now, what are we going to do with a pH of 2.87? Can we turn that pH somehow into the concentration of hydronium? Yes, we can definitely turn a pH into the concentration of hydronium. So we're going to go ahead and set up what I would call a RICE table. So the word RICE appears on the screen. That's an acronym for R, reaction. And then the next row of the table would be I, that stands for the initial concentration. And then we have C, which is the change, how things have increased or decreased. And then E is what you have at the end, or rather at equilibrium. Now, of these four chemicals in this reaction, remember that pure water is not going to be included in the Ka expression, so we can ignore any information about that. So what are we going to do with a pH of 2.87 so we can figure out what this number is right here? Well, if pH is equal to the negative log of the hydronium concentration, then the hydronium concentration is equal to 10 raised to the minus whatever the pH happens to be. So if on your calculator, you can go ahead and punch in 10 raised to the minus 2.87. Okay, see what you get. 10 raised to the minus 2.87. You should get a pretty small number. It should be 0.00 something. And if you've done that math on your calculator, you get 0.0013. And I talked about stoichiometry at the top of this lesson. That would be one of those relevant topics from Unit 4 on chemical reactions. Hopefully you can realize there's a 1-to-1 mole ratio between hydronium and the acetate ion, or the A minus ion. So I don't need to calculate the concentration of acetate. I know it's the same because of the stoichiometry and the 1-to-1 mole ratio. Now you might wonder, do we put this 0.10, does that go here? Well, actually that's the initial concentration. So let's go ahead and put that right there. And initially, let's pretend that this molecule has not ionized at all. So the concentration of hydronium and acetate is 0. You might say, but in pure water, isn't that 10 to the negative 7? Well, yes, it is, but we're going to focus on just the hydronium ions that are coming from this particular reaction. And so I'm going to go ahead and say it's very small, and so therefore 0. Now, what has happened in terms of the change? The change has to do with the concentration that has either gone up or down. So the acetic acid has gone down by a little bit, and the hydronium ion has gone up by a little bit. So we now have numbers on the right side of this table. There is no such thing as the law of conservation of mass. So we're not going to say that the acetic acid has gone down by 0.0026. No, we don't do that. We get the change based on the mole ratios. So with a 1-to-1-to-1 mole ratio, the change in acetic acid is exactly the same as the change in hydronium. It's just simply a decrease as opposed to an increase. Now, on your calculator, go ahead and do this math. What is 0.1 minus 0.0013? I'm assuming that if you do this math on your calculator, you're going to get 0.09 something. So when I did this on my calculator, I got 0.0987. There is a rule which is related to significant figures. It has to do with what you do when you add or subtract numbers in chemistry. Now, when you subtract two numbers and there are different amounts of decimal places, you always round off your answer to the one that has the least number of decimal places. In this case, 2 decimal places should appear in our answer. Well, how does 0.0987 round off to 2 decimal places? We can't just say 0.09 or 0.099. It has to just be 2 decimal places, and that would actually round to 0.1. It almost looks like the concentration of acetic acid did not change at all. Well, it did change, but by a very small amount. Remember that. That's going to come up in the next problem. The fact that the change for a weak acid in terms of the initial concentration and the final concentration is so small, that'll be something to pay attention to. Okay, let's go ahead and plug in these numbers in the final row of our little rice table. Let's plug them into the Ka expression. So 0.0013 times 0.0013 divided by 0.1. And if you do that in your calculator, you're going to get the Ka for acetic acid, which is about 1.7 times 10 to the minus 5. Something else we have to calculate is the percent ionization, and that is going to be the concentration of hydronium divided by the original concentration of the acid, and then times 100. So if we do this math, 0.0013 divided by 0.1, multiply by 100, and we get 1.3%. So let that sink in for a moment. About 98.7% of the molecules of acetic acid have not dissociated or ionized at all. Definitely a weak acid. Okay, here's another problem that relates to a weak acid, but this time we're not calculating the Ka. They actually gave us the Ka. And this time, instead of telling us what the pH is, we have to calculate the pH along with the percent ionization. Okay, how do we figure out the pH if it's unknown? Well, we're going to go ahead and start with our rice table again. We're going to write down, I've got it in the upper left corner of that slide. This is what we know. This time I can plug in information, but I cannot, I'm going to ignore the water. I cannot write this. I don't know what this is because it's not going to come from the pH since I don't know the pH. Let's fill in what we do know. Initial concentration of this acid. And again, this is called hypochlorous acid. It's a weak acid. It's not on your list of strong acids. I don't know what the change is, so I'm going to go ahead and call the change in hypochlorous acid X. So the hypochlorous acid concentration has gone down by X, and the hydronium and the hypochlorite ion have gone up by a certain amount. So I don't know what these numbers are, but I do know the Ka. So that's helpful. I'm going to go ahead and solve for X. We know that the Ka is 3 times 10 to the negative 8. We just don't know anything else in this expression. We have to solve for X. We are not going to use the quadratic equation. That's not something you'll see on the AP chemistry exam. And how do we get around this? Remember how I said that the change in the concentration of the acid was very, very small? Since the value of X is much smaller than 0.1, we can go ahead and simplify this expression by changing 0.1 minus X on the bottom to just 0.1. Well, that cleans up our math. Now we have X squared equals 3 times 10 to the minus 9. When you multiply both sides by 0.1, we'll take the square root, and then we end up with our answer for X. And since our answer for X is the concentration of hydronium, all we have to do now is take the negative log of that number. And if you do that, you get around 4 point something. So on your calculator, the negative log of 5.5 times 10 to the minus 5, it's around 4.26. All right, we have to figure out the percent ionization. So could we take this number, divide it by the original concentration of the acid, and then multiply by 100? All right, let's do that. And we get, wow, look at that. Look how small that percent ionization is. Over 99% of those molecules of HOCl, the weak acid, have not ionized, okay? So definitely a weak acid. Now, what you see on this slide is a summary of the two guided practice problems that we just did. Examine the data in the table below. Can you tell which acid is the stronger acid? Has a larger Ka, has a lower pH, has a higher percent ionization. Definitely, the acetic acid is the stronger of the two acids in this comparison. All right, now I want to just briefly, and I'm going to go kind of fast through this next slide series. I'm going to talk about bases, okay? This happens to be called trimethylamine. The water donates a proton to the trimethylamine right there, and it produces the trimethylammonium ion. That's the conjugate acid. This is completely analogous to weak acids. There's a little bit of a catch, though, in that when you figure out the concentration of this chemical here and you take the negative log, don't forget that the negative log of the concentration of hydroxide will not give you the pH. It will give you the POH, so you'll have to do 14 minus the POH to figure out what the pH is. So watch out for that. Otherwise, it's a very, very similar process. And so because of the similarity, I'm going to go pretty fast. Feel free, if you have to pause the video to absorb all this information, you're welcome to do that. So 0.1 is the initial concentration of the weak base. The other ones are 0 for now, and we have minus X, and plus X like we did before. We're going to go ahead and plug this into the KB expression so we can solve for X. We're going to make that simplifying assumption we did before, and that X is so small, I can ignore that 0.1 minus X on the bottom and just call it 0.1. Then we do the math, and when we solve for X in this case, and we take the negative log of 0.0025, again, this will not give us the pH. It gives us the POH. So don't get to do all this great work on the AP chemistry exam and then realize, the pH is not 2.6, it's actually 11.4. Okay, this is a base. Therefore, you should expect the pH to be higher than 7, not lower than 7. Now, for percent ionization, we can go ahead and take the concentration of hydroxide, divide by the original concentration of this weak base, and then times 100. And if we do that math, we see that the weak base is about roughly 2.5% ionized. All right, my next problem has to do with a solution of a weak acid. And we're going to add some water. We have 100 milliliters of a 0.1 molar solution of this weak acid, and we're going to add some water. So now we have 1 liter. Have we changed the concentration? Absolutely. We have changed the concentration by a factor of 10. You might remember Mr. Byrne yesterday talked about this equation, M1V1 equals M2V2. The volume of this solution has gone up by a factor of 10. Therefore, the concentration has gone down by a factor of 10. So what happens to the hydronium concentration in this flask on the right that has been diluted? What happens to the pH? And what happens to the percent ionization? I'm going to go again pretty quickly through these calculations, so feel free if I go too fast to pause. Here we have the data we already calculated for the 0.1 molar solution of acetic acid. I'm now going to calculate the concentration of hydronium for the 0.01 molar solution. And when I do this math, I get that the concentration of hydronium is less than what it was before. I think that makes sense to us. You added water, the concentration went down. What do you think is going to happen to the pH? Well, if you know anything about pH, you realize that the higher the concentration of hydronium, the lower the pH. So therefore, if you have a smaller concentration of hydronium, you have a higher pH. I think that makes sense to us. But you're going to be a little bit surprised by what happens in our next calculation. What happens to the percent ionization? If you take this number right here and divide by this number right here, you end up with a percent ionization that's actually greater than 1.3%. Now that seems a little strange to us. What happened to the percent ionization? It actually went up, but all we did was we added water. Did we make this a stronger acid? No, in fact, we just did something that has to do with, and this is from Unit 7, Le Chatelier's principle. Okay, so Le Chatelier's principle has to do with a shift in equilibrium. So we added water, and that caused the concentration of all three of these aqueous species. Again, we don't count the water as an aqueous species. It caused them to go down. Well, that naturally makes sense. We added water. But because the system was now put under a stress, the equilibrium position was trying to respond to that stress. And so it shifted toward the side of the equation that had a greater number of moles of aqueous particles to effectively counteract that stress. So as a result, the percent ionization actually went up for this more dilute weak acid. There is another way to explain this, and it's a mathematical way to explain this. This was a conceptual way of thinking about Le Chatelier's principle. Take a look at the Q, and the Q is going to be where we are right now. By diluting it, we have caused the concentration of all three of these species to go down by, in this case, a factor of 10. That means that our value of Q, which is the reaction quotient, is actually less. And when Q is less than K, again, this comes from Unit 7, when Q is less than K, it will cause a shift in the equilibrium toward the product side. All right, well, that was a little review of equilibrium. I do have one last problem to show you, and I'll go kind of quick, and then we'll get to our AP problem for homework. Here we have a titration experiment. This is from the 2016 AP Chemistry exam. And in this titration experiment, we have a before and an after picture of what the burette looked like. Let's talk about significant figures here. How do you read this burette? Every line on that burette is worth 0.1. So if I were to look at that burette and say, oh, it's approximately around 5.6, that would not be good enough. I'm going to have to record this to 2 decimal places, and I estimate that final digit, it's about halfway between 5.6 and 5.7. Over here, if I were to say that this burette is around 37.3, that's not good enough. I have to record that to 2 decimal places. The final digit, I think that meniscus is on the line. I'm going to go ahead and say that would be 0. So to record a burette that is marked off in 0.1 increments, you have to go to the 10th place. Let me go ahead and show you the answers. That was the answer to part A. Again, feel free to pause the video if you need more time to process. I'm going to quickly show you the answer to part B, okay, because we're kind of running over our time here. I'm looking at the clock and realizing we need to wind this up. So I'm going to go ahead and show you my answer to part B. I apologize for kind of rushing through this, but again, feel free to watch this and pause and you can kind of absorb this information. So there is the answer to part B. And then moving on to part C of this question. All right. So as I wrap up, we talked about a weak acid, we talked about a weak base, we talked about Ka and percent ionization. I now come to your homework for next time. And again, you can take a screenshot or you can pause the video. So Mr. Byrne will explain this question from the 2018 AP Chemistry exam with you all on Monday. And this is part A of the question. And this is part B of the question. So that would be what Mr. Byrne will talk with you on Monday about. All right, as I wrap up today, we're going to remind you that in the video description, you can see a link down below, tinyurl.com/helpfulchemresources. So check it out. Lots of good things for online learning and simulations and lots of good chemistry information. Thank you all so very much for watching. I hope that this lesson was helpful and that you enjoyed it. And we look forward to seeing you guys back on Monday for more AP Chemistry lessons. As a final note, if you are having any technology issues or you are aware of someone who does, please have that person or yourself go to cb.org/tech, and you can fill out a survey about your needs for mobile tools or connectivity. Again, this is Michael Faribaugh. Look forward to seeing Mr. Burns' lesson on Monday. Thanks for watching.